In this video, we're going to be looking at the end behavior of polynomial functions. By definition, polynomial functions are when you have non-negative integer degrees, exponential pieces here, in which you can write it in a form like this here. So a sub n, x to the power of n, a sub n minus 1, x to the n minus 1, all the way down to like a quadratic term, if you will, a linear term, and then a constant term. I do want to point out that constant functions like y equals 3 is a type of polynomial. A line like 2x plus 3 is a type of polynomial. And quadratics are also types of polynomials. However, we can have any degree, again, non-negative integers for those degrees, could go up to like 100, 1,000. It can be really, really crazy. So we need to know what these graphs look like. In order to do so, you're going to look at what is called the leading term. The leading coefficient is going to tell you the direction of the end behavior. N is going to give you the degree or the way in which the end behavior is either the same direction or maybe opposite directions. Let's look at a table here and see all the different possibilities. So if you have an even degree, meaning that that leading term has an exponential power of 2, 4, 6, something that is an even number, and your leading coefficient is positive, then your end behavior is going to be up and up, just like a quadratic. If you have an odd degree, 3, 5, 7, a line 1, if you will, that would have an odd degree of 1. We just don't write it, but it does have that. Then you have opposite end behavior. Think about the parent function, y equals x cubed. You can use that as kind of your mapping as an odd degree example. Same with quadratic as an even degree example. If you have a negative leading coefficient, then remember that's going to make this reflect over the x-axis, or positive y's become negatives and negatives become positives. So if that's the case, then our end behavior here would go down and down. Or if I have an odd degree, then I start up and end down. Now there is some notation for end behavior that we can look at with this like arrow notation. What this says is as x goes to infinity, your function values also go to infinity. Whereas if we look at this graph over here, as x goes to infinity, the values also go to infinity. Like that makes sense with the graphs. If I look at x going to negative infinity, then notice it says my function values need to go to infinity. Here, if my function values go to negative, or if my x values, go to negative infinity, then my function values go to negative infinity. And that's what that arrow notation means. If you end up taking calculus, you'll learn a whole lot more about those types of notations, and limits is what that is called. All right, let's look at an example here. I'm given this function. It's a polynomial function, and it's in factored form. I'm first going to express this in general form. Then I'm going to determine the lead degree, or the lead term, the degree, and then the end behavior. I'm going to rewrite it. And I'm going to choose to distribute this piece first, multiply out these two binomials. When I do that, I get x squared plus 4x minus x minus 4. And then I'm going to combine like terms to get 3x in the middle. I'm then going to distribute that first term. And since I'm multiplying like bases, I'm adding exponents. And then my coefficients multiplied together. So this would be my general form. It's in that form a 4x to the 4th, a 3x to the 3, a 2x to the 2. And then down here, notice I do not have these last two terms. Well, that just means that these two coefficients must be 0. All right, so then our leading term is going to be negative 3x to the power of 4. Our degree is 4. Our coefficient is negative 3. Since it's an even degree, I have two choices, either up and up or down and down. Since my leading coefficient is negative, my end behavior is going to go down and down. Now, if you didn't want to do all of this algebraic work, you can just look at the leading term of each multiplication piece. Meaning you could just multiply these pieces together, and you'll notice when you do that, you get negative 3x to the 4th. So that's a little bit of a shortcut if you don't want to write the entire general form, to just look at the leading term.